First of all, think about a bargaining situation. Think about, for example, a contract negotiation between labor and management. And typically what would occur is representatives from each would get together and they would have initial proposals perhaps, and those would be miles apart, and then they would over time negotiate and somehow come up with a contract. And these generally involve give and take, and they generally involve offers and counter offers and et cetera, et cetera. And so that's the sort of real life scenario in which bargaining occurs. Um, there are models to describe that, and these models typically involve non-cooperative games, where these involve the use of particular strategies and possibly with multiple rounds, et cetera, et cetera. And the cooperative bargaining model that was introduced by Nash in 1950 is different than that. The cooperative bargaining problem says the following. Let's sort of look at all possible outcomes of this negotiation process. So there are all sorts of specific processes, and the processes might vary in the details. But overall, what's ultimately important here is what are all of the possible outcomes that these parties can achieve, and what happens if they fail to agree. So this is the essence of a cooperative bargaining problem, that it strips away all of these details of process and focuses just sort of on the bottom line. So let's take a look at what a bargaining problem is. I'll come back to this in a sec. But this is sort of a picture of a two-person cooperative bargaining problem, where this is the payoff to player one, and this is the payoff to player two. So this might be labor, and this might be management. And B represents all of the possible combinations of payoffs that they could achieve via some particular negotiation process, or every conceivable payoff vector or two-tuple. Then it also specifies what's called a disagreement point. That is, what happens if they fail to reach an agreement. So this is the substance of a cooperative bargaining problem. Again, just sort of reducing it to the bottom line and specifying what happens if they fail to agree. So a cooperative bargaining problem is a pair, BD, where B is a subset of Rn, so this involves N players, N-person bargaining problem. And this specifies the set of all possible combinations of payoffs that the N players can achieve. And it specifies a disagreement point, that is, what happens if the players fail to agree. So that is a cooperative bargaining problem. And we're going to assume some structure that we're not going to look at arbitrary problems. We're going to assume that sort of minimally they have the following three properties. First of all, B, you could call this the bargaining set, but that's actually, that name has been used in a different context. But for our purposes, we might as well refer to this as the bargaining set. So the bargaining set B is assumed to be convex. That means convex, closed, and bounded. So when we come back to our picture of a typical bargaining problem. Convexity means that, I don't recall if we've seen this before, but it means that there are no indentations. And we know, for example, when we talk about preferences being convex to the origin, that there are no indentations. Right? And that sounds like a rather formal mathematical property, but it's reasonable for the following reason. That we can rationalize the convexity assumption by saying, let's assume that this point is a possible outcome of the bargaining process, and let's assume that this point is a possible outcome of the bargaining process. Okay? So either this are two possible outcomes to the bargaining process. Well, one way to resolve this negotiation might be to flip a coin, to randomize between this possible outcome and this possible outcome. And if we allow that randomization, that tossing of a coin, then in effect, every combination between that point and that point, any what's called linear combination, every point on the chord that lies between that and that could be achieved via this randomization process, where we let the probabilities or the weights vary. So for example, if probability 1, this outcome occurs, then these payoffs would be achieved. If with probability 0, this outcome occurs, but probability 1, this outcome occurs, then this could be achieved. And if we toss a fair coin, then the midpoint between them would be the expected payoffs. So we can rationalize that if this point is in the bargaining set, if this point is in the bargaining set, and we allow randomization over these payoffs, that every point in between should be in the bargaining set, or every what's called a convex combination should be in the bargaining set. So that is one way of rationalizing the fact that B should not have any indentations, because if it did have an indentation, then if we randomized between this and this, then that wouldn't be achievable. So allowing randomizations convexifies. It fills in all of the indentations, so to speak. Okay? So that's not a very very objectionable assumption. That's rather compelling if we allow for randomization over outcomes. Closedness is a technical assumption. We just assume that B contains its boundary, okay? So that every point on the boundary could be achieved. It's not as if there's a bargaining process, a negotiation process that would allow us to get infinitely close to the boundary but not on it. So that's a technical assumption, that we assume that B contains its boundary, it's closed, and that it's bounded. That is, it doesn't go off to infinity in any direction. If it went off to infinity, then that's effectively saying that someone could achieve an infinite payoff, and that doesn't seem reasonable. So we assume that the maximal payoffs of all of the players are limited to some extent. Okay, so those are the three assumptions we impose on B. This allows randomization. This is a technical assumption, and this basically says that payoffs can't be infinite. We also assume that D it's possible that the players would fail to reach an agreement, and that in fact we would end up at the disagreement point. That this is a feasible or an achievable outcome of the negotiation process. That negotiations break down and each party takes its disagreement payoff. And then just to make this interesting, we also assume that there's some vector of payoffs in B such that everyone would receive strictly more than every player would receive strictly more than its disagreement payoff. Okay? So there's some incentive to bargain. If some player would never be able to achieve more than its disagreement payoff, then it has no real incentive to negotiate at all, right? So this is just to say that the problem is non-trivial. Everyone stands a chance to gain. And in fact, there's some possible outcome in which everyone would strictly benefit rather than resort to the disagreement outcome, okay? Okay, a solution on a class of games is simply a rule which associates with each game in the class some feasible outcome, some feasible payoff vector. Okay? And we're focusing on single valued payoff vectors. So we're not looking at something like the core of a cooperative game where it specifies a whole set of possible outcomes. Here, a solution will make a precise recommendation for how this situation should be resolved, or how the bargaining should be resolved. Okay, and so this is sort of a rule. You could think of this as, for example, a mediator's rule. That if these parties come to the mediator, then this is the rule that specifies the outcome that the mediator recommends to the parties. Okay. Okay, one particular solution, and this was the original solution introduced by Nash when he discussed the cooperative bargaining problem, it's come to be known as the Nash bargaining solution, or the Nash solution. So I'll use N to denote the Nash solution to the problem BD, the Nash solution maximizes the product of payoff gains. So this is relative to its disagreement payoff. This is player one's payoff gain. This is player two's payoff gain over its disagreement payoff, et cetera, et cetera. And you look at the product of these n payoff gains, and that's